compound Q is this, and because it's written in this horrible structural formula, I think it's worthwhile right from the beginning just carefully rewriting it in a more helpful skeletal formula so you can see clearly what's going on, so you're confident what the functional groups are. So just going through it one carbon at a time. So you get CH3, CH2, and then CO always means a carbonyl group. Okay, so CO means that, and then CH2, and then CHO means an aldehyde group. So it's that. And I think if you're clear about that right from the beginning, then you have much more chance of not sort of making mistakes in this question. So the first thing it wants us to do is to write an equation for the reaction of that with aqueous acidic potassium dichromate. So of course this is about the fact that ketones cannot be oxidized, so that will be unaffected, but the aldehyde can be oxidized to a carboxylic acid. So we just write the usual type of equation with a magic oxygen to represent the oxidizing agent, and that will produce something which is virtually the same. The ketone group is unaffected, but the aldehyde group is changed into a carboxylic acid, and so we get that. So that's the first bit. And then it wants a sequence of reactions that would demonstrate that it has an aldehyde group and that it has a ketone group. Now the aldehyde one is easy because you should know a specific test for aldehydes, which is the Tollens test. So for the first one, so this is B part 1, to show that it has an aldehyde group, you can just warm with Tollens reagent. So learn the whole test, warm with Tollens reagent. You may possibly get penalized if you just say add Tollens reagent. So warm with Tollens reagent. And don't just say it will form a silver mirror, because you need to make it clear what that signifies. So you need to say if it forms a silver mirror, that shows there's an aldehyde group, or only if there's an aldehyde group will it form a silver mirror. And that deals with the aldehyde part of it, because no other group will do that. So you can't just use the dichromate reaction and say, oh, that shows there's an aldehyde group, because although it's the aldehyde group that's reacting there, alcohols would do that. Primary and secondary alcohols would also do the same colour change with dichromate. So that's why Tollens is important. So warm with Tollens reagent, you get a silver mirror only when an aldehyde group is present, and therefore that would demonstrate that. Now the tougher one is part 2, which is to demonstrate that there's a ketone group there. Because the obvious thought would be, oh yeah, 2,4-DNPH, 2,4-dinitrophenylhydrazine, reacts with aldehydes and ketones to show that, to form a yellow-orange precipitate. The trouble is that you've got both in this compound. So it's going to react anyway with 2,4-DNPH because you've got the aldehyde group there. So that doesn't actually provide in itself any evidence that the ketone group is there, because you're going to get a yellow-orange precipitate anyway. So the way you get round that is you say, right, do this reaction first. Okay, so either oxidize it with dichromate or with Tollens reagent, because remember that does the same thing, turns it to a carboxylic acid. So do that first and then test it with 2,4-DNPH, because we already know it has an aldehyde because we've done this test. So you say after you've treated it with Tollens reagent, or after you've heated it with aqueous acidic potassium dichromate, then you do the 2,4-DNPH test. So you just add the compound, and the fact that you get a yellow-orange precipitate shows that there must be a keto group there, because the aldehyde's been destroyed. So that was a tougher question, but that's what it was getting at. Part C is asking us about the reaction with aqueous acidified sodium cyanide. This is again a reaction you need to know all about, so if you start making it up you're going to get it wrong. You just need to learn these reactions. And the key word in this sentence was excess. It said there was excess cyanide, and That's usually a clue when they use that word to suggest, oh, it's going to react more than once. And of course it can do, because what you should have learned is that acidified cyanide will react with aldehyde groups and with ketone groups. So if you've got excess, it will react with both. So it's very simple. It's just addition across the carbonyl group. So you're going to react with 2H plus and 2CN minus, 2 of each, so you can react with both groups, and you just form the hydroxynitrile groups. So here you get OH and CN, where the ketone group has reacted, and here you get OH and CN, where the aldehyde group has reacted. And if you've learnt your reactions, you remember that that's nucleophilic addition. So it's addition, there is no other product, and so that's all you have in your equation. Then it asks how come the product is actually a mixture of isomers. So this is not because it may just have reacted with one or the other. It's told you it's excess, so that's shouldn't be an issue. What it's about, and what you always need to look for when it talks about it being a mixture of isomers, is stereoisomers. Obviously there's no EZ issue here, there's no alkene groups, but that and that are chiral centres, and that's what it's about. Notice the original compound had no chiral centres, because these didn't yet have 4 different groups around them. So what you need to say is that 2 new chiral centres are formed during the reaction. Okay, that's not quite the same as just saying there are 2 chiral centres in the product, because if they'd been there already, that wouldn't have the same importance. It's the fact that 2 new chiral centres are formed during the reaction, and therefore you're going to get a mixture of the non-superimposable mirror image forms, or the optical isomeric forms at both chiral centres. So remember that at this one you can get either the right or the left-handed isomer, and then whichever one you've got there, you can get either the right or the left-handed isomer at the second centre. So in other words, there are 4 possible combinations: right, 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 left, left, right, left, left. So 4 possible isomers could be formed in that reaction. Okay, so then it asks for the mechanism of the reaction of the aldehyde group specifically, so you don't need to do it for the ketone group, of the aldehyde group with the acidified sodium cyanide. So this is straight off the syllabus. So if you don't get the marks in questions like this, you're going to end up being really annoyed with yourself, because this is just stuff you learn in advance and you just trot it out on demand. So there aren't that many questions like that. There's an awful lot of thinking has to be done in these chemistry papers. So when you get one that you can learn in advance, you've got to make really sure that you have learnt it and can do it. So this is just the standard nucleophilic addition mechanism, and the key thing, remember, is that it's because that is polar that it attracts in a nucleophile. So you've got to show the dipole. The nucleophile is the cyanide ion, and you have to remember that it's the lone pair on the carbon that does the attack. In fact, both ends have lone pairs, but you just need to know that this is the one that's the stronger nucleophile. So it attacks, and that means that there's a curly arrow going in there, showing that that lone pair is going to be used to form a new bond to the carbon. And because carbon can only have 4 bonds, it can only accept that incoming one if it breaks an existing one. So at the same time, it does that, which signifies the pi bond breaking and that bonded pair of electrons becoming a lone pair on the oxygen. Okay, so what you get then is not yet the product. At the moment, just an intermediate, which looks like this. So you now have O minus just singly bonded with a new lone pair, because that electron pair that used to be the pi bond has now become that lone pair there, and you have the new bond to CN there. So that's the intermediate. To complete the reaction, it's not going to stay like that. Remember, alcohols are not acidic, so that O minus ion is not a stable thing. It's going to pick up a proton. And in this case, it's very simple. Because it's an acidified solution, you have H plus ions floating around, and so you can simply do that. Okay, show the curly arrow, meaning that that lone pair of electrons on the O minus is being used to pick up the H plus. In other words, the O minus is acting as a base and picking up a proton, and that completes the reaction to give you the hydroxynitrile. Okay, so it's a relatively simple mechanism, and you've just got to make sure that you've learnt it in advance.